This is the repetition or the basic part of your study prior to this theory of structure. Learn how to sketch qualitative deflected shape. This is, I think this is new for your knowledge. This is just I think just a matter of how to translate the deflection in understandable manner. Okay, and in relation with bending moment diagram, and then understand how to simplify your analysis using principle of superposition. Okay, for principle of superposition is the most crucial part for analysis. Okay, since we will have indeterminate structures, which means you can't solve a structure using uh, equilibrium equation. Just only using equilibrium equation, you can solve a structure which have quite a few numbers of reaction on the structures. That, for example, if you have a fixed and pin support, okay, you will have five reaction, and then you will for equilibrium equation to complete, you can solve only a simply supported, which is if you have a pin and a roller in one beam, right? For example, if I can draw it here, okay. Okay, for example, if you have a pin and roller, it shouldn't be any problem in solving these structures, since we have only two reaction here and then one translation here. So you can solve it using equilibrium equation. There is no problem on it. But if you have a fixed support and a roller, for example, you will have a three reaction here and rotation, and then you have one reaction here. So you can solve it using equilibrium equation. Just using equilibrium equation, you need to do another method, which is for example, stiffness method or flexibility method to solve this part. Okay, so for this kind of structures, you need to do a principle of superposition. Okay, I will discuss it later on. Okay, it is just for you to, I think, to understand. You need to understand the concept of indeterminate and determinate structures. Okay, for this part, if you have quite lower than three reaction on the structure, you can call it as determinate structures. But if you have more than three reaction, you will call it as indeterminate structures. Okay, there is a difference between that. Okay. Oh yeah, I provide the analysis carried out to determine the external forces, reaction forces, which is internal forces, and then shear force, bending moment in beam and frame, is a force in thrust and also in frame, and deflection. Okay, this is for determinate structures. Okay, the structure is determinate if the number of unknown forces equal to number of equilibrium equation. So this is what I said. Okay, if you have a cantilever beam, okay, cantilever beam, you will have three reaction here. Okay, and the number of equilibrium equation would be summation of force at x is equal to 0, summation of force at y is equal to 0, and the summation of moment at equal to 0. Okay, you will use this what is this? Okay, you will use these three equations to solve the reaction in cantilever beam. As you can see here, it is enough for summation of fx. We will use this translation. Summation of y, we will use this translation, and the moment rotation, you will use this reaction. Okay, you have enough number of equilibrium equation to solve the reaction. But if the structure is not equal or less than the number of it is not a stable structures. For example, if you have pin support in cantilever beam, and then your reaction will be like this, right? Okay, this end of the beam, if there is no constraint in here, it will start to rotate, going downward. It's rotate, so it is not stable. So you need, if you have a stable structures and you have the same number of reaction towards the equilibrium equation, there is no problem in solving that. This call it as determinate structures. Okay. For analysis and beam frame, draw a free body diagram. First, you need to draw the free body diagram and use the equation of equilibrium to solve the reaction forces. Construction, bending moment, and as a force diagram, draw a quantitative deflected shape for the frame by connecting the deflected shape of each beam. Okay. Okay, this is the first example. Determine the reaction on the beam as shown and draw the shear force and bending moment diagram. Okay, as you can see here, this is a pin support. Okay, and then we have a roller here, and then the equation of equilibrium will be equal to the number of reaction. So the structure is stable. There's no problem with that. So if you have an external forces acting on the particular beam with 60 degrees of angle, so you need to transform these uh, forces, external forces, into y and x axis. So by using trigonometric equation, or I don't remember the equation names, so you can use sin, cos, and tan method, and then you can get the value of external forces acting on the structures. Okay. Okay, as you can see here, we have another external forces, which is 67.5 kilonewton meter. You can solve it easily by using equilibrium equation. There's no problem with this. Okay, by using summation of force at x equal to 0, and you can get the value of ax equals to 135 kilonewton with anti-clockwise movement in the positive direction. Okay, you can get the value of by, and then you can get the value of ay. Since we have only 3 reaction on that particular structures, so you will have only 3 reaction, which is ax, by, and ay. So if then you already get the value. So this is your first assignment: bending moment and shear force diagram. Draw the bending moment and shear force diagram and submit via e-learning. Okay, I have provided the place for you to submit the submission link. You can do the submission there. Okay, the submission will be due date will be in 2 days time, which means before our next session, which is on Thursday. I need to have the submission by that. Okay, which means the last submission will be tomorrow night at 12 p.m. 12 a.m. Okay, please do that. Okay, then the sign convention for drawing shear force and bending moment diagram. For positive external axial forces cause tension. Okay, uh, what do we know about this is that if you have a beam and the external axial forces causes the tension, so is it compression or is it this one is compression? Okay, okay, this is tension. Obviously, this is tension, and this is compression. Okay, positive shear force happen when external forces push to the left section and section up and the right section down. So this is just a matter of the understanding uh, on how structures work. Okay, positive bending moment bend the beam concave outward. Okay, if there is a moment and there is an axial positive axial forces, it will cause the structures to bend. So this is basically one of the concept for deflection. Okay, okay, for qualitative deflected shape is an exaggerated sketch of the deflection of the structure and the load. This is useful for visualization, but it's only an approximation, so it can be used as guide for drawing bending moment diagram. This is just when you look at a problem like this problem, first you need to imagine how what will happen if you have this kind of external forces acting on that structures. Okay, obviously if it is going down, it will go down, and then the rotation will rotate negatively Okay, so it will going upward a little bit. Okay, and then there's a uniform distributed load. So again, it's going downward. So the structure is going down. Okay, this is just a approximation or assumption on how the structure will react based on different different external forces. So this is just an imagination. If you don't have this kind of imagination, it will be quite hard for you to understand engineering. So I believe that all of you have uh, this imagination that is quite enough to complete your undergraduate program. See? So another example, the compound beam shown in fixed at A. Determine the reaction at A, B, and C. Assume the connection at B is spin and C is roller. So we will have two reaction here. Wait a minute. Okay, so we will have to, this is B, we will have a pin support, so there will be two reaction here. And then for C is roller, so we have one reaction. And at A, we have fixed support, so we have one, two, and three. Okay, three reaction. So we have eight reaction. We have six reaction. So segment BC, we have anti-clockwise. So we need to divide the structure into two parts since it is indeterminate structures for as a whole. So you need to divide the structure into two parts. So due to um, Newton first law of motion, if there is force acting on it, there will be another force acting on it to remain the structures in equilibrium position. So if you divide the structures into two parts at B spot, so the reaction will be, we will have two reaction here. Okay, so this is the kind of uh, based on the principle of law of motion. Okay, this is if you have the assumption of going upward for the support, so you need to have another support if you cut the structures into two parts. Okay, so if you do equilibrium equation, you can solve the value. Okay, you can have by bx. So you can do a revision on this topic. This is just a repetition from your mechanics of material or engineering mechanics. Okay, so based on the result, please draw the shear force and bending moment diagram and qualitative deflected shape. So this is another assignment that you need to submit tomorrow. Okay. Okay, this is an example. Analyze the frame as shown. Then draw shear force, bending moment, and axial forces diagram and the qualitative deflected shape for the frame as shown. Okay, this is frame structures. Okay, you can see the support. We have one pin support and one. Okay, this is pin support. So there will be two reaction, and this is roller support. You have one reaction. Okay, the external forces will be 19 kilonewton here. And then you have UDM 30 kilometer per meter. Okay, I hope this will not be a problem in solving UDL. So you should know how to solve UDL since this is kilonewton meter. How to get one point load. Okay, by the times with another meter. So you can cancel a meter. So the meter will be the length of the UDL. So there will be no problem with this. Okay. Solution. So summation of Fx equals to 0, summation of Fy equals to 0, summation of moment equal to 0. This is just an equilibrium equation where you have all those three equilibrium equation. You can just do a revision on this, slowly pick up what you have left before. So you can do the exercise later on. Okay, just look at the procedure right now. So we just do a revision right now. Okay, and you do summation of moment at d equal to 0, and you can get the value of the reaction in this particular frame structures. Okay. Okay, for frame structures, I still remember my PhD is my master degree. When I did my master degree, I used a frame structure like this one to analyze their its vibration data. So when I get the vibration data, I can compare with my finite element model, and then I can know where the damage in this frame. So this is just another topic. Just yeah, these are the same structures that I use. Okay, you can solve the equation one by one, part by parts, element by element. There's no problem with that. Remember, if you have a reaction here, you will have an opposite reaction. So what happened here is that this is the reaction that will happen. Okay, and then you can draw the shear force diagram, any moment diagram, and energy diagram, and qualitative defective shape in separate.
Doctor, I'm sorry to interrupt you, but I have a question. Can you go to slides before? Okay, so no, the other one. Yes, okay. So you can see the 90 kilonewtons force over there, and
Mhm.
I just have a question. I have realized that after we finished with the first beam, that 90 kilonewton has disappeared, and I didn't really understand why did that happen.
Has disappeared.
Yes, you can go to the next slide. Yes. So, for example, we have a 90 kilonewton force here.
Mhm.
After the first joint, I couldn't. I mean, it just disappeared. I'm not really sure. I think there is a reason, but I just don't know what is it. That's why I'm asking.
It's still here, 90 kilometer.
Yes. Okay. So after that, shouldn't the 90 kilonewton go, or we should add it to the another to the other member.
It is already removed by these forces here. 90 kilometer. It is balanced out here. Okay,
Okay, but
the force
okay.
here is
So for
balanced out.
example, the 65 kilonewton was also balanced, but we still added it to the other member. Do you know what I mean? We have another 65 kilonewton, right?
Yes, here, here.
On the
Okay,
y direction, yes, but and then we also added it to the upper member. You can see at B.
yeah.
Can you see 630 kilonewtons just below it a little bit? That's
Okay,
65
okay.
kilonewtons, right? Yeah.
Okay, okay.
So
This
why
is
why didn't we do the same thing with the 90 kilonewtons?
okay. This is not uh uh quite difficult. Okay, if you have a frame or truss, remember a frame is acting as a beam. Okay, if we remove the column support, what the support here? What would be the support here? So that is why we have 65 here, just to remind us that the column here, the column part is the support of the beam, right? Okay, do you understand that? So for this
Uh,
part, for 90 kilonewton, it's already balanced out here. So the support here, the connection here is not a fixed support or anything because it is a rigid connection. So for rigid connection, we usually we remove the axial forces acting on the beam parts. So that is why we don't have 90 kilonewton on the beam section. We do have 65 since it will acting as a support, a fixed support, which is a rigid connection. We react as fixed support. Okay.
uh, yeah, I think I understand a little bit, but I'm not really sure. So we just removed it because of the member BC. We just analyzed the supports, its supports. So
Mhm.
65 is acting on the support itself. but the 90 kilonewtons are not acting on the support; they are acting axially on the member. That's why we removed them,
Mm-hmm.
because they are acting on an axial uh, way. That's why
Mm.
we didn't put the 90 kilonewtons and we put 65 kilonewtons again.
Yep.
Is that the reason? So
Yep.
what about the CD? I mean, 205 kilonewtons are also acting axially on CD, but
Mm-hmm.
we still use the 205 kilonewtons.
Yeah, it is the same because it is a frame. So if you have a frame, this is the rigid connection. So
Okay.
it is the same. Procedure happen here and here.
Um, so we just removed the forces that acted on the x-axis, which is the 90 kilonewtons, because it balanced at the first time. So we don't add them when we
Uh,
are analyzing the rest of the members.
yeah, it is already balanced, and this is a frame. So usually for beam parts for frames, we don't analyze the axial forces. Axial
Oh, okay,
forces
okay,
meaning the exist the force that I take alongside the beam parts.
okay. And for the 205, even though that it was axially affecting beam CD, we
Mm-hmm.
did use it because it was not axially affecting BC, right?
Mm-hmm.
Is that the reason?
I don't understand the question again.
Yeah. Okay. I think it's okay. I'll just try to practice again on frames.
Okay.
Yeah, it's okay. Thank you.
All right. Okay. Let us continue. Thank you for the question. Okay. For example, this is another example. The site of building is subjected to wind loading that creates a uniform normal pressure of 15 kilopascal on the windward side and a suction pressure of 5 kilopascal on the leeward side. So determine the horizontal and vertical components of reaction. Okay, this is due the effect of wind. Okay, you can do the analysis later on because this is another subject where we consider the wind load. Okay, okay. Okay, for the wind parts, I will not discuss more. Okay, you can just do the revision on this subject. As you can see here, if we have an UDL, you need to transform to remove the meters, so times with the meters, times with the length, so you can get the point load there, and then you can do the analysis later on based on the angle. You can do the analysis. Yeah. Okay, by applying equilibrium equation, still by applying the equilibrium equation, you can solve these structures. Okay. Okay, this is just a revision, just a matter of to know how to solve the structures using uh, equilibrium equation. But we will need to discuss next week, I think, for force method, which is for indeterminate structures, is pretty much a new thing to you. So this is just a revision. You can do that later on. Okay. So by solving the part one by one, you can get the value of the reaction. Okay, for this is the principle of superposition. Okay, the principle of superposition state that the effect of multiple loads acting on a structure is the algebraic sum of the reaction under those load individually. This is true for particular condition. The structure must not deform significantly under load, and geometry must stay in the same. So the geometry, which means the shape of the structures. Okay, the structure must compose a linear elastic material. It must obey Hooke's law. So for elastic parts, I think I have explained on the Hooke's law, what we do on based on plastic analysis and elastic analysis. Okay, if we have this kind of graph, okay, this is the part of elastic. So we do the elastic analysis based on this graph. But I think towards the end of this to the end of this subject, you will learn on plastic analysis. Okay, for this subject, we will just discuss on the elastic manner. Okay, So the principle of superposition is this. The principle of superposition makes analysis easier by allowing the consideration of one load at a time. So if you have multiple load, you do the analysis one by one by removing first the unwanted the load one by one. Okay, so this is the primary structures. So we do the analysis one by one, which means we do the first analysis by having this one point load, and then we do another analysis on this one point load. Once the direction for each load are determined, they are simply summed to obtain the total, which means if you have the value ay2 and then you have the value of a11, so you need, if you want to have the total value of reaction acting on the primary structures, you just added the two values. Okay, you can get the real reaction on the structure. So this is the principle of superposition. Okay, so where you have multiple loading and then you separate it by loading. So another concept is by separating the reaction or the redundance. I think you will learn that part on flexibility analysis. Okay, where we have two redundant. For example, we have fixed support and a cantilever thing, a roller here. So you have this one as the extra parts of equilibrium equation where you don't have the equation to solve this one. So we'll take this one as another part of the primary structures. So you will do the analysis here. Okay, if you have a 2 point load, we have one position and then another position, and then we need to do another position here. Okay, this is another topic. It is the same procedure where you have um, the equation there. If you have uniform distributed load here, okay, and then you have a moment here, so you need to separate it into two parts. So this is the principle of superposition. I think you understand that it is pretty straightforward. Okay, linear relationship exists among load, stresses, and displacement. Two requirements for the principle to apply: material must behave in a linear elastic manner. It is, as I said earlier, the geometry of the structure must not undergo significant changes when the loads are applied. So small displacement theory. So if the loading is big, and then it will affect the structures pretty much. So you can do this is the principle of superposition. If the value of external forces is small, you can do the principle of superposition. But normally we don't have uh, uh, such a bigger load on our examination, so there's no problem with that. So in summary, in general, beams and frame members have internal axial forces, internal shear force, and internal bending moment. So you should know what is this. Okay, okay, you can read this later on. Okay, we have end our first part, so I will give you around 5 minutes break. Okay, we continue later.
Thank you, sir.
Okay, we continue a little bit. This is a trust for analysis of determinate structure for trust members. So it's quite tricky a bit. Um, but we can go on with it. Okay, no problem. Okay, for this objective, for this topic, you need to understand the assumption of ideal trust and how real trusts differ. Okay, able to analyze determinate plane trust by method of join. So beam frame and truss, we have different kind of analysis. So for trust members, we will need to analyze the axial forces acting on each members. So I think you know that. Okay, assumption for analysis of trusses: all members are connected with frictionless hinge or ball joint. So the part the connected each part of the beam of the truss would be by hinge and ball joints. All loads and support are applied to the joints. The centroidal axis of each member passes through both adjacent joints. Together, this assumption constitute an ideal truss subject only to axial forces. So this is the part, as I said, the truss will go through an axial forces. If you have a truss, like if you have, if you have truss like this, which is uh, the parts where we have, oops, oops, oops. Okay, so the axial forces is the forces acting inside the members. Okay, real truss do not quite meet this idealization. Real truss are usually bolted and welded to gusset plate. So additionally, the weight of the members are distributed along their lengths. Okay, these deviations are called secondary forces and can be ignored if they are small compared to idealized primary forces. Okay, that's why we have a zero joint member, zero members. Okay, that is the part that we will go through later. Okay, this is the example of connection between trust members. Is it either ball and joint nut, or is it by this kind we have a plate cover it in bolt and nuts. So this is the part that is joined together. So we have bolt and nut here. Okay, analysis of plane thrust by the method of joint. In the method of joint, the axial forces in the members of the truss are determined by applying the equation of equilibrium to each joint of truss. So usually we don't have rotation. So we just has this is the summation of fx equal to 0, summation of fy equal to 0. Okay. The joint is selected with no more than two unknown forces, and the equation of equilibrium force in x and y are applied to determine the unknown. It may be necessary to find the reaction forces prior to selecting a joint. It is standard to present tensor forces as arrow away from the joint, okay, and the compression force as into the joint. So it is similar. If it goes like this, yeah, it is a tension. If the members goes the axial forces goes like this, it is compression. So there's a logic thing here. So this is the first example. Two unknown member forces at joint B, one unknown reaction at joint C. Okay, the unknown members and force and joint member force and two unknown reaction forces at point A. Okay, so this is spin support. You have two reaction and then you have one reaction here. So by having this reaction and angle, you can actually determine the axial forces acting on the beam members, on the truss members. Okay, so the solution, okay, just a matter of a trigonometric equation where you have sine, cos, and tangent. So there's no problem with that. You can look at this, how to solve it. Here we have, I already provide the solution for each joint. So we need to do the first joint and then the second joint and third joint together one by one, and then you can complete the analysis. Okay, this is for joint C. So what the reaction will be? So we have 45 degrees of angle, and then we have the axial forces here, and then the reaction here, and then the other forces here. If you have, for example, here the axial forces acting this way, there will be another axial forces acting this way. So that is why we have 707.1 Newton there. Okay. Okay, this is for joint A parts. So we have all this reaction. So we just have we should, if you assume the reaction at A is going this way and going this way, but if we complete the analysis one by one, we can change the direction later on. So we assume that the positive reaction is going to the right and the positive reaction is going upward. So if it's going in the opposite direction, we just change into negative numbers. Okay. Okay, for free body diagram, each pin shows the effect of all the connected members and external forces applied to the pin. So that we can complete all the analysis and put it in one trust members. What the members experience tension as the forces, there is a forces going away from the members, and this is a compression part where the forces is going towards the members, and this for the tension part. Okay, by having this analysis, you can know which part you need to strengthen and which part you need to have a good material properties for compression and tension. So for free body diagram, each pin shows the effect of all the connecting members and the external force apply to the pin. So we can put it in this free body diagram, all the forces, all the reaction, okay, in this but one particular structures. Okay, this is another example. Analyze the stress as shown. Uh, so what will happen? We draw all the forces acting on the beam. So this is just an assumption on what will happen to the beam. So we do the summation, the equilibration of fx equal to 0 and fy equal to 0. Since this is stress, we do not consider the moment. Okay, all this part one by joint method, where you do the analysis one by one based on the joint parts. Okay, this is first we do the joint, this joint A, and then we do the joint B, C, and D. Okay, we do the analysis one by one. Okay, and then once you have completed all the analysis, you can put it in one free body diagram. Okay, this is another example where we have multiple parts. So that is why I said for trust member this is quite tricky, since we have multiple parts that we need to do the analysis one by one uh, at the joint. So if we have more joint, we do more analysis. Okay. So this is one joint. You can read this one later, or you can do this as an exercise. And if you don't have the understanding on this part, you can contact me, or you can contact me anyway. Okay, this is for joint G, and then this is the solution for joint B. I don't do the explanation part because this is just a repetition. I can just show you what actually happened. So this is the part that you do the analysis one by one and obviously the joint. Okay. Okay, for zero force members, this is the part where for the beam part, for the truss part, there will be a zero members, which is if you do remove that particular member, the structure is still stable and can perform well. So for case one, the two members at joint C are connected together at the right angle and there is no external load on the joint. The free body diagram at joint C indicates that the force in each member must be zero in order to maintain equilibrium. Okay. The free body diagram of joint C indicates that the force in each member must be zero in order to maintain equilibrium. So this part can be called it as zero, since there is no axial forces acting on these external forces acting on this join. So there's a few cases. If you have members in um, in parallel in one line, so this is a hinge or the connection part. So if you have a force, external forces here, so there will be axial forces acting towards towards the objects, and then you have another part that balance it out. So if you do have the balance it, so if you put another member here, this member will equal to zero since this part is already balanced. You don't need to transmit towards these members. But if you have a thrust members that acting like this, going this way, so you just imagine that there is laser forces towards upward, going upward here, so the structure will not balance out. So if you put another members here, okay, the forces would be going this way because it want to balance the reaction here. Okay, okay, this is another cases. Zero force member also occurs at joint having a geometry as D. No external loads acts on the joint, so the force summation in the y direction, which is perpendicular to the two co-linear members, requires FDF is equal to zero. So this is what I said. This member is equal to zero since this is parallel. So the forces here is already balanced out. So there's no forces going this way because it's already balanced out. So this is actually is equal to zero. Using this result, Fa is also zero member as indicates by the forces by force analysis of joint F. So Fc is also equal to zero since it is already balanced here. It's going it's already balanced here, so there is no forces going upward here or in any direction. Okay. Another example, using the method of joint, indicate all the members of the truss that have zero forces. So by having just do a visual inspection, we will know which part of the truss is equal to zero. Okay. Okay, we do the analysis and then we can know which part of the members is equal to zero. So you can just look at this, but by using an assumption, you can know which part of the beam of the truss is equal to zero. Okay, for procedure for analysis, check for static determinacy, identify zero force member. So this is the first part. Identify the zero members by using a visual expression by having a characteristic. If you want to know more on which part of the trust members is equal to zero, you can just Google it or you look up at YouTube. There will plenty of the video on how to know which part of the trust members is equal to zero. There is no problem with that. Since I probably provide two cases, which part of the trust is equal to zero or it is not equal to zero. Okay. Then determine the slope and of the incline members. Draw the free body diagram of the truss. Select a joint with no more than two unknown forces which are not collinear. If no such joint exists, find the reaction first. So if there is no joint exists, you need to find the reaction first. Okay. Draw a free body diagram of the joint. It is convenient to assume all forces are tensile, which means you assume all the members going away from each other, not going towards each other. So you assume all the members are in tensile. Determine the unknown forces by applying the equation of equilibrium. So we do have two equilibrium equations. So since we consider moment for thrust. So negative signs mean the forces is compresses when and acts into the joint. Okay. Repeat this step for the rest of the joint until all desired unknown are found. So this is what I said. We do the analysis one by one at the joint. Check your work using equation you have not used yet. If you have not yet used the equation of equilibrium for the whole thrust to find the direction, you may use this. Otherwise, use the remaining joint equilibrium equation. Okay. Analyze the thrust as shown. Calculate support reaction first. what reaction would be on the trust. Okay, and then we do the analysis one by one at the joint. Okay, we can get the value of it by using the angle part where you have a triangular method where we have if it is three distance 3 4 5, you do the analysis one by one. Okay. Okay, if you do have 3 4 and 5, you don't need to have the angle part. Okay, please, this is just a mathematics. And we do analysis one by one at the joint. We can complete the analysis at each members of the trust. Okay, this is another example. Is it unstable? That is unstable because the B plus R is less than 2J, which is it is unstable. Okay, we need to have it is equal, then it is stable. If more than that, it is indeterminate. Okay, we do the analysis one by one. So I already provide the result. You can do analysis first, and then this is just another example. You can do the analysis, and I already provide the answer. Okay, if you have problem in solving all these example, you can contact me. So this is just a repetition. I hope that your previous lecturer have already um, supply you with the knowledge, the fundamental of solving the trust. Okay. Okay. In summary, several assumptions such as frictionless or joint are made while analyzing the trust. You should understand this assumption. Plain trust may be simple, compound, or complex. So you should be able to identify each of these. The method of joint is used to analyze trusts. You should be able to use this method. So the method of joint is by solving the part one by one at the joint, right? I hope that for joint part there will be no problem since we will look at indeterminate structures later on. So this is the basic one. Uh, I hope you do understand. If you do not understand, you can contact me. Right? Any questions so far?
Hello,
If you don't,
doctor.
yeah,
Doctor, will you be uploading the recordings to e-learning?
I can hear you well.
Sorry. Doctor, will you be uploading the recordings to e-learning?
Yes, I will do that.
All right. Thank you, doctor.
All right. If I do not upload it in e-learning, you can remind me later on. Or I should just share the link. Okay, share the link of my Google Drive, and then you can ask permission to just to look at the video. Okay.
Okay, doctor.
Okay, I should stop recording first. Okay, if you don't have any question, I see you on Wednesday, Thursday. Thank you.
Thank you, doctor.
Right.
Thank you, doctor.
Okay.
Thank you, doctor.
Welcome.
Thank you, doctor.
Welcome.